Of course, there was a typo, so we're ready to resume. I correct a typo on the grading formula. Of course, it's the min, not the max. Otherwise, everybody would have 6, which would be nice, but is not true. So the internet is based on packet switching. Here is a small fraction of the internet, which is a snapshot of the EPFL network. What is visible on this? We see computers. It's an old-style picture. Most of them would be tablets or smartphones today. Those cheese boxes are routers. And you see two kinds of things. At least I see two kinds of things. I see names, lrcmac4.epfla.ch. And then I see numbers. Those numbers are called IP addresses, exactly. So those are 32-bit numbers written in the style of the 70s. So one group of 8 bits is written in its decimal representation. So a block is a number between 0 and 255. I say it's the style of the 70s because today we would not write it in this way. How do we write bits today? With hexadecimal digits. So addresses today are written with hexadecimal digits, but those IP addresses, which are called the IPv4 addresses, are written in this style. So what we see is addresses and names. That's the first thing that networks have to sort out, is all networking mechanisms must use addresses. Addresses are the equivalent of zip code or postal codes for the postal system. If you send a postcard to somebody, you need to give the street address and a number that corresponds to the city. In Switzerland, the number is not very informative. In other countries, in the UK or Canada, the number is really the number, the zip code is really the number of a block, so it identifies where, with a very high accuracy, the recipient is. That's the same thing here. Those addresses are exactly that. They're identifying where in the internet the computers are, with many caveats that we will discover a bit later, in particular the special addresses. Now, the bad thing about the internet is that the internet started with the wrong thing, which is an address space on 32 bits. Why do I say it's wrong? Of course, I can say now it's wrong. When it was done in the mid-70s, I did not say that, I must admit. I was still a student, anyhow. Why do I say now it was wrong? Number of devices. What's the number of devices? How much? How much is it? With 32 bits, how many devices can you address? 2 to the power of 32, which is 4 billions. Now, the population of the Earth is about double, and each of us has several devices. Plus, we need addresses for things like routers, etc. So this is a bit short. When this was done, of course, nobody invented when the internet was done that it would be used for everything like it is done today. We thought it would be for more advanced and scientific purposes, but we didn't imagine that each of us has several devices with several addresses here. So that is too short and has been replaced by something which is longer. This is 32-bit. Now this is 128-bit, 128 bits. And this is called IP version 4, and this is called IP version 6. There is no IP version 5. I mean, there was one, but it's not really an IP. It's called protocol ST2. So this is, in principle, the normal IP addresses, except, as we will see, they are not used a lot. Most of the internet today uses IPv4, with a fraction of it is moving to IPv6. And one of the problems we will discuss is the fact of having those two address systems is a bit of a problem, because those addresses are incompatible. When I say incompatible, that means if I create a packet, remember the mental model of the internet is we create packets that are like postcards. If I write in the packet an IPv4 destination address, then it can go only to a system that has an IPv4 destination address. If it's sent by a system that has only an IPv6 source address, for example, it doesn't work. So it's more than just the address format. It's really the packets are different depending on the addresses they contain, which is what I say here, they are incompatible. That's a design decision of the Internet Engineering Task Force, the standards body of the Internet. When they decided to expand the address space, they decided also to create a new IP, a new Internet Protocol version 6. It was not just the old one with expanded address space. So it's like if the post office would do that, if they expand the numbers that are 4 decimal digits in Switzerland, if say they, after decades of population expansion, we're as large as Germany, so we need 5 digits, but then all the postcards that have, you need different postcards and different pens to write those 5 digits. This is what is happening in the internet with IPv6. We have also seen names. Names are originally meant as being human-readable substitutes for addresses. And we'll talk more about that, but here is a very first thing you need to know. So the names are the end, the most significant thing is at the beginning, and the more general thing is at the end. So the last element of a name is called a top-level domain. The two, it's made of letters. 2-letter domains are country codes. All the others are something else. So at the origin, there were a small number of domains, like the .com and the .ch, and now anything can become a domain if you pay enough money. For example, somebody paid for the .sucks, and which is just a way to do blackmail on companies, which one of the problems of those names. Now, an important thing to realize about name is illustrated in this little diagram. If you go from your computer to a web server, from this one here, so you click on a web page. What happens when you click on a web page? Well, you have a web page that says the name of the server. Now, the name is not directly used by the IP protocol. Names are not present in the information used to transfer packets across the internet. You need first to go to a directory service, which is called DNS, Domain Name System, to translate the name to an IP address. So this computer must have the relationship with a DNS server, normally that of EPFL, but you can use Google's DNS server if you prefer. Most companies don't like you to use their DNS server, except for Google, who's very happy to have you use them because they will learn information about you. Then going to the DNS server, the computer here, the software, in fact, will know now the IP address of this machine, and then what is sent is an IP packet that contains as destination address the address of this machine, right? So in the IP packet header, the information that is used to transfer this packet across the world to the final destination, the name is not used. The name may be present in the text of the message, or may be absent, depending on what the text is, but is never used to transfer packets. So names are human-readable forms, but the machines, the routers, they use IP addresses. How does the web server know the IP address of your web browser? When you contact a web server, you first go to the DNS to learn the IP address of that machine, then that machine responds to you. How does they know your IP address? Because we put the IP address in the source, exactly. So this one, when we send a packet, we put not only the destination, but also the source. And the source is used primarily by the destination to know how to respond to you. So that is the network layer. The network layer is how about organizing routers such that they can read addresses, IP addresses, and send the packets to the correct destination. There is something more mysterious, which is called the MAC layer. The MAC layer is sometimes called the link layer, and it is also a network, but it's not called the network layer, but it's also a network, and it's used to interconnect a small number of devices. Now, why do we need a special thing to interconnect a small number and another one to connect a large number. The reason is purely historical. The first networks were like this. And then the internet, if you think about the name, I mean, we don't call it the net. It's not the NP protocol, the network protocol. It's called the internet protocol. So the name internet comes from the fact that at the beginning, the job of the internet was not to make a network, but was to interconnect local networks. Local networks are the things that we discuss here. A local network is what you obtain when you connect several devices with what is called today a hub or an Ethernet switch. It's a small device that you can buy at Migros. It's a box that has a power supply, and it has plugs, sockets, where you can put your jacks into it, and with Ethernet cable you can connect everything. That's the wired version. The wireless version is called a Wi-Fi base station, which is mentally the same thing, even though the physics is very different, but mentally is the same. You can connect many devices together. It's called a local area network. This is how computer networking emerged. So computer networking at the beginning was about having a computer that is connected to a number of terminals for people to speak to the computer, send their commands and their programming jobs, a printer, a disk, and a few things that were all interconnecting using a local area network. And when you want to interconnect those, this is where you have introduced routers. If we would do it from scratch today, so there would be an atomic war that wipes out entirely all the technology of the Earth, except in our brain we would remember everything, probably we would not do a MAC layer. We would simply use the network layer to interconnect everything. But it's done, and one of the things we will discover in this course that what is done is very hard to undo when it's done in the billions. So you have billions of computers that use the MAC layer and the IP address v4, for example. It's very hard to move that to anything else. We will see also that the MAC layer has a serious advantage compared to the internet, to the network layer, is that it's meant to work without any configuration. You will learn, perhaps a bit painfully at the beginning, that for an internet to work, you need to put a lot of configuration of information in all the devices. At the MAC layer, the idea is that this is not needed. And it's not needed, and it's possible if you do a very small scale stuff. We will see how, a bit later how this can be magically done. In particular, a big difference between the MAC layer and the network layer itself, or a common thing, is that they have addresses. As I said, the MAC layer is also building a network, so it uses the same principle. If I send, it uses packet switching. If I send a packet from A to B at the MAC layer, it's often called a frame, but it's also sometimes called a packet. All this is computer science. So in computer science, contrary to science, if there is science in it, it's not a science. So in computer science, the terminology is shaky. So people tend to forget what the previous generation did. So you have to be very careful with the terminology. I will try to give a few fixed points and warnings. The word packet is one of those weird things. So what is exactly a packet? A packet is very often meaning a packet of the network layer, an IP packet. If it's a packet of the MAC layer, we call it a frame. If it's a packet of the TCP layer, we call it a segment. But sometimes people use different words. So a MAC layer packet contains a destination address, just for the same reason as an IP packet contains a destination address. But the difference is that the destination address is a hardware address. So it is, here it's written in hexadecimal, it's 48 bits, which gives all those hexadecimal numbers. And it's a hardware address. You can program it if you want. We do that in particular in the lab when we have virtual machines. But in principle, when your smartphone or your PC comes, the Ethernet adapter has a hardware address. The Wi-Fi adapter has another Wi-Fi address. In principle, you don't change it. So this address means nothing. In fact, it means something. The first half is normally a signature of the manufacturer. So you can see whether this is Cisco or Apple. This is probably Apple. This is probably a Cisco address. But that doesn't help much. So the address in particular doesn't say whether this device is RTPFL or not, which is normal because it's a hardware address. If I am with Wi-Fi here, my Wi-Fi base station, my Wi-Fi Ethernet MAC address on my smartphone is the same if I go home and I'm served by Swisscom or by my own Wi-Fi network at home. So this remains the same, but as long as you're connected to a given local area network, then it's up to the network to discover, and we will see how this is done. But the address is used to know whom the thing is destined to. So, for example, when my PC speaks to the router, if they're both on the same LAN, my PC needs to know the MAC address of the router in order to send a packet to the router. We will see how this is done. That's the purpose of the ARP protocol here. The mental model of the MAC layer is exactly the one that's explained here. What is explained here? Here, we send a packet and it has a given destination address. And all devices can see the packet, and they decide to copy it only if the destination address is their own. This is how people thought in the 70s. It's hard to imagine today. But this is how people thought in the 70s. They were living in a nice world where security was not an issue. There was not Russian or other entities that were trying to infiltrate the network. You thought that if you send a packet that has a destination MAC address that is not for you, then you don't take it. Perhaps this is how Switzerland was 30 years ago. The rest of the world certainly not. But this is how the internet was designed. That's the mental model of the MAC layer. You create a packet, you put the destination address, you throw it away into your LAN, and whoever it is destined to will recognize it and will take it. And this was because the original MAC layer was on a shared medium cable. And this, which is more or less what we have with Wi-Fi today. Of course, today we don't do that, although the mental model is the same. But today, the base station, for example, will analyze a number of things. If you have not given the password that is here, the base station will not accept your packet, so it will do a number of additional things, but we will find the same principle. So a local area network, that's the terminology, is a set of devices that are connected at the MAC layer. For example, here are two distinct local area networks. If the picture is exactly this one, they cannot communicate with each other. If you want them to communicate with each other, you use the internet, which practically means here, you put a router. The router is on both local area networks, so this router needs a Wi-Fi interface and an Ethernet plug, an Ethernet cable to the switch, and then the router will be the thing in between. That is a mental model. That's the way to think of how networks are organized today. You have local area networks interconnected by routers. The mental model does not always match the physical reality of the boxes that you can touch, of the physical things that you can put your finger on, and that you will put your fingers on in the labs that we do. In particular, what very frequently may happen is that this box and that box are the same. At home, if you have an ADSL modem, it can serve both as a Wi-Fi base station and an Ethernet switch and a router. So those three things, in fact, may be combined in the same box. But this box has the three functions, even though they are not visible. That's one of the difficulties of reasoning about the systems we're working with, is the fact that the functions are sometimes not visible, and the literature that describes how to use the system sometimes is completely obfuscating things. So it's very hard to understand exactly what is happening because of the literature that describes the system. What we will try to do is recognize the functions. Here, this function of a router means something that interconnects two local area networks. Here, function of a base station or a switch is something that interconnects systems inside the same local area network. One practical thing that we are immediately confronted with when we organize a network is the addressing scheme and the concept of masks. So we'll come back to those things when we discuss in details next week the IP layer. But for getting started, we need to understand this. If I come back to my question here, what do we see on this picture of the EPFL network? We see addresses, but perhaps you see more. They all? They all part of the same subnet? No, hopefully not, because the EPFL is large, and a subnet is typically a few tens, maximum 100 devices. But we see that, I mean, the IP addresses, they all look the same. They all start with 128, 178. Right? So there is a prefix here. So IP addresses are structured. They are structured in two ways. There is first a prefix, for example, 128, 178. This is used by the rest of the world to recognize that this is EPFL. This is not the network mask. This is not the subnet that I want to talk about. So we'll come back to that part a bit later. But if I look at perhaps what you said a minute ago is right for this part here. If I look at all the addresses that are here, they have the first 3 words, so the first 24 bits are the same. Here. It's not by accident. It is because this is the way that IP has found to put together systems that are in the same local area network. Remember that IP is used to interconnect local area networks. So in doing this interconnection, systems need to know whether they are in the same local area network or not. If they are in the same local area network, there is something special that happens, right? If A here and B are in the same local area network, they can communicate directly. If A wants to send some information to B, what does A have to do? What is the main technical thing that it has to find? Find the MAC address of B. Right? They communicate directly, so if I communicate directly with you, that means we are in the same local area network. All I need to find is your MAC address, because finding the MAC address, remember the mental model of the MAC layer is, I just need to know your MAC address, I throw the packet into the MAC layer, with the magic of your MAC address, it will reach you. If A talks to C that is here, well, it's a bit more complicated. A needs to send to the router, so A needs to find the MAC address of the router. So A needs to know first that it has to send to the router, and it needs to find the MAC address of the router. So when, of course, it's not you and me who does that, it's the operating system, the software and the machine. The software and the machine has to know whether the destination is in the same subnetwork or not. How do we do that? It is using the analysis of the IP addresses. At EPFL, all IP addresses that are in the same subnetwork have in common the same 24 bits. So this magic number, 24, is an equivalent description of what we call the subnet mask. EPFL subnet mask is 24 bits. So those two addresses, 128.178.71.34 and .71.23, are on the same subnet because if I look at the first 24 bits, they are the same. In contrast, this address, 84, is not in the same subnet as this one. So when this computer sends a packet to this address here or to STI-SUN1, we cannot send directly. You will need to do the complicated thing here. The subnet mask at EPFL is very nice. It's 24 bits. Why is 24 nice?
It's 3 times 8, so we just cut it. 3 triplets, so 5, so 2 by 5.
Yeah, because it matches nicely the decimal representation. It's a multiple of 8. Right? At ETH, it is 26, which is not a multiple of 8. So whenever the mask is not a multiple of 8, you need to use your binary calculator to transform the bits, the decimal sequence, into a sequence of bits and apply the mask. So the mask is a number, which is in fact a sequence of bits, which has ones in the position of the subnet, the thing that is used to identify the subnets, and zeros otherwise. So this is assuming that I do a bitwise AND. If I have this address, if I translate it into a string of ones and zeros, if I do the bitwise AND with this, I will find something that will be equal to 128.178.71.0. Right. If another system which has the same mask, does the same operation, and the result of those two operations are the same, then that means we are on the same subnet. So why do we have this clumsy operation? Why don't we say simply /24 instead of saying this? That's for historical reason. You could as well say the prefix at EPFL, the subnet prefix at EPFL is 24 bits. Now the bad news is you need to configure a machine with this. Your machine doesn't know whether it's at EPFL or not automatically. Well, we'll see their automatic way by contacting a configuration server and so on, but you need somebody, either mechanically or you manually in the lab, to give what is the mask of this interface, so that it's part of the configuration information. Right? And if you configure it wrongly, things will go wrong. For example, if you think the mask is 16 bits, what would happen?
Sometimes we might get it right, but sometimes we might think some computers are in our network, but they're right.
Sometimes we might think some computers are in our local area network, and this is not true. For example, if this machine is configured with a mask which is 16 bits instead of 24, and it wants to send a packet to STI send1, it will say, oh, this guy is in my subnet, so all I need is to find the MAC address of this guy. So we'll try to find the MAC address. How do you find the MAC address? Typically, you send a broadcast. You send a message to everyone asking who has this MAC address. But the broadcast is done only in the local area network. In the local area network, nobody has this destination IP address, so nobody will answer. It will not work. So this guy will say destination unreachable. We will see that there are ways to fix the problem other than correctly configuring, but in principle, the correct way means we need to configure that. That's one of the examples of configuration information that is needed for IP to work. For IP to work, you need that every interface has its own address. The address doesn't come from heaven. It doesn't come from the manufacturer, like the MAC address. It must be given to you based on where you are. If you're at EPFL now, you must have an EPFL address, and you must have the correct network mask. So that is why we say that IP is not plug and play. For IP, you need to do something. Of course, when you came to EPFL this morning, you did not configure into your iPhone, which would be hard, or into your computer, which would be easy. But I'm sure you did not, perhaps with some exceptions, you did not go into ipconfig or something like this to set up your network mask. So we will see that there are so-called configuration servers, DHCP servers, where what your computer does when it comes to EPFL is first contact a server to obtain that information, and only when it has that information, it is able to communicate in the network. So this is the MAC layer, and how the MAC layer is visible in the IP layer in the form of network mask. Now the layer below is the physical layer. The physical layer is the easier for us because we will totally ignore it, apart from one or two properties that I will discuss now. The physical layer is anything that transforms our world, which is bits, into physical entities, physical signals that are typically radio waves, either on cables or on optical channels, which are optical waves, which are the same nature as radio waves, or on wireless channels. There are also acoustic waves that are used to transfer signals underwater, and a few other exotic things like this. For us, the physical layer is simply something that takes bits or blocks of bits and transfers them to another end into something else. It's still visible to us in the form of performance. What does the physical layer give to us? It is a channel with a given bit rate. The bit rate is called if you take the communication theory or the information theory courses, it's called the bit rate. In computer networking, it's invariably called bandwidth. Right? If you take the information theory course and you call it bandwidth, they will not like it. But in the context of computer networking, people have confused bit rate and bandwidth is in hertz. It's a physical thing. You do a Fourier transform of the signal, and in which part of the spectrum does it live? It's bandwidth. The larger the bandwidth, the more bits you can transfer per second. But it's not all. There is, of course, for example, on the additive Gaussian channel, you have this relationship between the bandwidth, B, and the capacity in bits per second of the channel that depends on the signal-to-noise ratio. So the larger the B, the higher the capacity, but there's also, of course, the signal-to-noise ratio that is very important. For us, that means that the physical layer is not transparent. It has a limitation, which is how many bits per second it can transfer. And one peculiarity of the internet is that it's able to work on everything from very little. Those are the speeds we had at the origin. At the origin in the 70s, we were even below kilobits. We were talking of hundreds of bits per second. We will see examples of when TCP was designed, it was as a reaction of a collapse from a few tens of kilobits to a few hundreds of bits per second. Now we are more in the terabit per second range. Now, the capacity or the bit rate of a channel is important for the design of protocols such as TCP because it impacts the timing. If I transfer a file from a server to me, I would like that this happens as quickly as possible. But how quick is quick? So for example, how much time does it take to send 1 megabyte? So the capital B for me here means byte. So byte is 8-bit. At 10 kilobit per second. So 10 kilobit per second is what you have when you're in the middle of France on the cellular network. Right? Or France or a place that has a very poor cellular telephony connection. If you have a calculator, it's easy. Otherwise, you can try to guess. I close in 5 seconds. And the majority gives 800 seconds, which is correct, so which is a lot of time for what we're used to. So the concept that's illustrated here is that the transmission time, so the keyword here is transmission time, well, is inversely proportional to the bit rate and proportional to the number of bits you have to transmit. Of course, transmission time is not everything. There are lots of other things that in practice will make the time to transfer that amount of data much longer than the 800 seconds we have found. Another thing is propagation. This is another space-time diagram where now time is horizontal. And we see that if I transmit a signal on the cable, for example, or in the air, this signal doesn't propagate instantly, but it propagates at the speed of light, or radio waves, which is the same for all waves. It's not the same speed in all materials. In open air or in a vacuum, it's 3 times 10 to the 0.8. In glass, it's much less. In copper, it's also less. And as a rule of thumb, it's 5 microseconds per kilometer. That's very fast. If you see me here, by the time you see me, it looks instantaneous compared to the speed of the sound. But it's not completely negligible either. For example, if I transfer a file from New Zealand, New Zealand is about exactly at the other end of the Earth from here. So if I send a request to a web server that's in New Zealand and the response comes back to me, I've done a round trip time over the Earth. How much time does it take? I close in 5 seconds. Okay, you should see the results now. The majority is right, as often, but not always. The time to send is effectively 200 milliseconds, assuming the distance is 40,000 kilometers, which is perhaps a bit optimistic. Probably the signal will take more time, but in the lab 0, you will do some tests with New Zealand. You can find the time to get there. You will see it's a bit above, but not much above. It's a bit optimistic because, we don't go in a straight line to New Zealand. We go, by which mechanism do we reach New Zealand in the internet today?
Either the ocean or satellites.
Fiber under the ocean or satellites, exactly. So that's more if we use fiber under the ocean, so trans-ocean cables. Satellite links are typically even longer. The distance is typically longer if we use satellite links. So if we put all of this together, we see that when I transfer one block of data, for example, 1 kilobyte, which is one packet, one IP packet typically, the ratio between the propagation and the transmission time differs depending on the technology. We see that there are technologies that are dominated by propagation. This is, for example, 1 megabit per second over a very long distance. Well, 1 megabit per second for accessing a video server that's at the other end of the world is something that can happen. In that case, you see that you're dominated by propagation. In other circumstances, like if you have very high throughput and you're very local, then you're dominated by transmission. This will have an impact on the way TCP is designed, for example. TCP is designed in a way to work well in all those situations. But as we will see, there will be optimizations depending sometimes on one of the operating points. The throughput is about the same, is a quantity we will often use also. It's about the same as the bit rate, but it's the useful bit rate. The bit rate is how many bits per second a channel can transfer. Ethernet, for example, is typically 100 megabit per second for standard Ethernet, 1 gigabit per second on most modern installation, 10 gigabit per second over optical systems. But you never get exactly that rate when you transfer data. Why? Well, it's explained here. One of the reasons is the protocol overhead. When I transfer an IP packet, there is an IP address. The IP packet, as we will see, is inside a MAC layer packet that has also a MAC address. All of this takes space, takes bits, so we lose a few percent, typically 10 to 15% of the transmission capacity is wasted by those overheads. The larger the packet, the less the overhead. The smaller the packet, the more the overhead is in proportion. But another thing is the protocol inefficiencies that I will illustrate not on the pigeon example, but on the example of the stop-and-go protocol. Here is a very simple way of how TCP works in some situation. I'm transferring a packet from a machine A to a machine B, right? And sometimes the packet can be lost because of propagation errors, for example, that normally should not happen very frequently, but the bit error rate is never exactly zero. So if there are enough errors, it can be that the packet is corrupted and cannot be reconstructed with the error correcting codes at the destination. So if that happens, the packet is lost. What would TCP do? It will detect the loss and retransmit. How do you detect the loss? Well, one way to detect the loss is to ask for an acknowledgement, which is shown in green here, whenever I send a packet in red. And the stop-and-go protocol is a very simple protocol that you can do in an application, for example, if you don't use TCP, or is a primitive way of seeing how TCP works, where I send some data, I wait for an acknowledgement to come. If the acknowledgement does not come, if the acknowledgement comes, then I send the next packet. If the acknowledgement does not come, I start a timeout here, and after some time, which hopefully is longer than the round-trip time here, I will time out and detect that the packet is lost. That's a very simple retransmission protocol that we find practically everywhere, which is how we detect and repair packet losses. Now, if we do it exactly like this, we can compute what is the loss of efficiency due to this protocol. What is lost in this protocol? Well, what is lost is the time here. I am sending data, then I wait and do nothing, right? If you had an employee sending packets and you say to this employee, send it, wait until the acknowledgement comes, and in between do nothing, right? It's a great job, but it's a bit boring. So here, this is inefficient, and this lack of efficiency can be captured by the throughput. I can compute the throughput for this protocol by simply counting over time how many read bytes I receive divided by the total time. And I will see that it is equal to B, which is the bit rate, how many bits I could transmit if I would be always transmitting, if there would not be this protocol. And I see that it's B divided by 1 plus two things. One is the overhead. L prime over L is the length of the acknowledgement. The acknowledgement is not useful data. It's just data I'm sending back to make the thing work, but it doesn't contain my video image that I'm trying to download, for example. So that's part of the overhead. That's easy to understand. And the other thing is the time wasted because of this. And the interesting thing is that this time wasted can be expressed as something called the bandwidth delay product. Is the product of the bit rate B multiplied by 2D. 2D is the round trip time, which you see here is the time to go from A to B and to go from B to A, which is typically, but not always, the same. So if you assume it's the same, that gives 2D. So this is called the bandwidth delay product because it's the product of the bandwidth, the bit rate B, by the delay. And it has an interpretation. It is the number of bits that are in the wires, that are in flight. When I transmit something, if I transmit here, for example, a stop, I want to say to this guy stop, then the times that will come is here. So this is the inertia of the internet or of a transmission system. And the bad news, of course, it is dictated by 2D. Now, 2D is the speed of light, so it's given by physics, so we cannot change it. We can do faster network, we can do faster bit rates at terabits per second or even multi-terabits per second, but the speed of light will always remain the same. So a protocol like this is very efficient if the bandwidth delay product is large. We can look at the different cases we have before. If I look at the different cases and I look at the throughput I would have for this protocol, I see that in all cases it's very good. So the bandwidth delay product is not against me, except in this one. And in this one case, if I would use this, I would be using only 3.8% of the capacity of my link, which of course would be vastly suboptimal, so we would need to do something about it. We will see what TCP does about this thing. Voilà, that's the alarm signaling the end of the course. So thank you very much and see you tomorrow for the lab.